As you can see, the title of my presentation is The Pace of the Green Transition, the force acting upon and probable scenarios. This is still a resistant development within the goals of our Resist Center in St. Petersburg. And part of this work is already published, submitted to Technological Forecast and Social Change. We are still waiting for the opinions of the reviewers. Very important to point out that this presentation is not a forecast about green transition. On the contrary, I will make an exercise about a kind of backcasting, what happened in the past and what forces are acting upon, are impending the green transition. The green transition is happening, in fact, but is happening in a velocity, in a pace very, very slow. And I will expose to you which forces are these. Okay. Before discussing the causes of the slow-moving rate of adoption of renewable energy source, I want to show to you some graphs about the worldwide unfolding of the usage of the complete set of the energy source in the last 30 years, since the first IPCC meeting in Sweden in 1990. Then my date of reference is 30 years ago, in 1990. Important to observe that since then, we have had 27 conferences of the parties. The last one was in Egypt last year, with apparently very important decisions. But if you look in the discussion that we find in every meeting, we can easily conclude that there is no real science, and mostly what we have are empty political discussions. So, more on this later in this discussion, okay? Let's go first to the graphs, 3 important graphs. The first one, okay, then in the first graph, you can see the unfolding of all energy sources during the last 30 years. Here are missing the names of the black curve is oil, the red curve is coal, the green curve is gas, and below you have the green curve is hydropower, the brown curve is nuclear, and the 2 last ones are wind and solar, okay? And then we can see that the contribution of the low carbon sources is very small and very important. All fossil fuels are increasing, have increased in all this during the last 30 years. Then as we can see, global energy consumption is not stagnant. It has grown substantially in the last 30 years. Oil consumption grew 42%, gas consumption just doubled, and coal consumption grew 73% until 2003, after which it remained relatively constant with a drop in 2020 in the same way as the other source because of the COVID. Okay, very important. This astounding growth was too quickly for renewables to keep up. This is the main point here in this slide. Now, the same curve, but now presenting the share of the different energy source, not the total energy production. Here's the share. Above all, the black one is oil, and in the following one is coal, okay, orange. The green curve is gas. Then we have in brown the hydroelectricity, hydro energy. The brown is again nuclear, and the 2 last ones, the upper one is wind, and the last one is solar. we can see that wind and solar only grew substantially after 2010. So now some important conclusions about this graph. The information that stood out the most in this graph is the expressive decline in the old share of the planetary energy consumption, from 40% to about 31%. In other words, a reduction of about 22%. Very important to observe that such decline was not a case of energy substitution. Oil was not substituted for other source. The share of the contribution of coal fluctuated up and down, but remaining roughly constant. And the share of gas consumption only increased 20 to 25%. The contribution of wind and solar only grew significantly after 2010, and the contribution of both to the global share has not yet reached 5%. Okay, then if we sum solar, wind, and even the growth of gas, they not reach the reduction of oil. Then the reduction of oil, the main drop, the drop in oil consumption lies not in technological substitution, but lies in technological development, the third branch of the triple causation that I will discuss in this presentation. I will present to you a collection of causes for this phenomenon that I call the triple causation, three different kinds of force that are acting upon the green transition. Now, this graph is the representation of the share of all low carbon sources together, okay? Low carbon energy is defined as the sum of all sources, nuclear and renewable source, which include hydropower, solar, wind, geothermal, wave and tidal, and bioenergy. We can see that the unfolding of this curve, we have a light increase from about 14% to today 18%. This is a growth of only 4 percentage points. But it is important to point out that the 2 digits share, as a 2 digits 18% in the graph, is mainly due to the contribution from hydropower and nuclear energy, both far larger than the share of the other renewable considered together. As can be observed, the rate of progress since the 90s is not impressive. By 94, we are getting about 14% from low carbon source, but today, 3 decades later, 30 years later, the share has increased only by 4 percentage points. In other words, the move upwards is indeed happening, but relatively too slowly, probably much more slowly than expected and desired. The observed increase, about 28% since the 1990, implies in the yearly growth rate of about almost 1% a year, which in turn means that in 2030, we may reach a share of only 25% from low carbon sources. This is pure extrapolation. So, maintaining the same trend, we can calculate a share of about 43.6% in 2050, still below of the expected green transition, when the share of low carbon source should surpass the line of 50%, as expected by many people. But considering the actual circumstance of the global energy supply chain, mainly political causes, as well as other circumstances that I will comment on, the triple causation, this figure, this increase may not happen as desired. Okay, we can say the above estimations about the growth rate of renewables are based on pure extrapolation. And we know that extrapolation is not a good forecasting method. But the results meet other model-based forecasts. As for instance, a model of myself that I published in 2010. I work with 10R diagrams of curl, alien, renewables, and I worked with logistics substitution model, and I have demonstrated it only by 2075, the share of renewables plus nuclear might reach 50%, only in 2075. In another very recent work published by Professor Akaev and his co-author Beloborodov, they, using mathematically oriented scenario writing, demonstrated that the grid energy transition with the achievement of the Paris Agreement will be possible only by 2060, when the share of renewable energy in the total energy balance will reach between 40–50%. Then you can see that we have some similar forecasts. But, as we say, this forecast may not be realized if we consider a series of other circumstances that have not been considered in practically all the discussion in the IPCCs carried out so far. The roots of the observed low pace of adoption of alternative energies or renewable energies can be seen under the perspective of a threefold causation. The first one, socio-political causations. I will show to you what is this. Second, political, strategic, and territorial causation. Third, the technical scientific aspects with three main branches. The first one, the technical, is the increase in efficiency. The 3.2, very important, four very, very important technological drawbacks. I will comment one by one. And the 3.3, the technological improvement. This last one is the only one hope, the only one force that can act against the others. All others, this first point, second point, third point, 3.1 and 3.2 are contributing to the slow pace of the energy transition. But the point 3.3, the technological improvement, can act against this force. Okay, now about the socio-psychological force. We know that we evolved in a world in which the dangers that threatened our survival were immediate, easy to perceive with our own senses, and impacted just our local community. We know that our brain is wired to perceive menaces coming from our external surroundings, around us. In contrast, most of today's greatest dangers developed over decades require spatial monitoring and scientific analysis to understand really in depth. And moreover, they impact not just our local community or region, but impact the whole planet. Our brains are not wired to sense this menace. Okay, we can say that adaptation to rewire our brains is no longer an evolutionary problem, but a behavioral development spanning a few generations. And the whole discussion about climate change is something that has developed mainly over the last 30 years. In other words, just over one generation. And can add to that, that the generation that is still in charge of this planet still does not seem motivated to prioritize the overcoming of these serious environmental problems. We know that economic and political interests are the major motivations of human behavior. It's interesting to point out that this behavior, which originates in our mental structure, has been the target of analysis by some psychologists who designate it as cognitive biases related to climate change. I found a lot of reference about the publications about the opinions of the psychologists about these cognitive biases. There are a lot of biases. I cannot describe each one here. But the question is whether in 2 or 3 generations we will be able to observe a substantial change in the human existential practice that can overcome these mental biases. We don't know the answer to this. Okay, then analyzing the socio-psychological aspect, the result is that this behavior is an unconscious disregard for the effort of decarbonization. Okay, then to the second point about the political, strategic, territorial causes. And this is a very complex system of interwoven aspects. I will try to point out the most important points. First one, what I call an strategic mistake. It is about the Western inconsistency in the energy strategy, in my point of view. They underinvested in the energy they actually use today, which are, we know, fossil fuels, based on the magic thinking about the energy of tomorrow, renewables, which come in the day after tomorrow. See, for instance, what is happening today in Europe about the problem with energy and all the problem that we know is happening today. This problem will not happen if they have think differently in the past. So now the role of politicians. We know politicians are more committed to persuade at any cost, supported by the news or fake news, than committed to inform using science to analyze and decide. They insist in the myth that technological innovation allows endless growth in consumption of materials, energy, and land on a finite planet. So, about the relationship about space, population, and the economy. In this paper, in this publication, we have scrutinized the usage of low carbon source among the 21 different countries. And we could demonstrate that the expected green energy to be obtained by solar or wind energy has the greatest effect in small countries, countries with small territory and small population, where there are not so energy-intensive industries and have the suitable availability of sun and wind. Not all countries have such favorable combination to use wind and solar energy. I will show to you in the next table the top 10 countries leading in the share of energy using low carbon source. Okay? Very quickly, we can see I have here 10 countries, the 10 top countries. I added some European countries, United Kingdom, Portugal, Denmark, Greece. And when we look to the share here in the 1, 2, 3, in the 4th column, we see the Iceland is the leader, but Iceland becomes energy from hydropower. And we see Norway and Sweden come next. And so a big source is hydropower, but Sweden also nuclear. See, for instance, the case of France, 48%, 50% for low carbon source, but the greatest part is nuclear energy. But the case of Brazil, the big part, big contribution is hydropower, and so on. We see that in all these countries, the big share, the big contribution is either hydropower or nuclear energy. The contribution of solar and wind is still very, very small. Then, when we look for these top 10 countries in producing energy, here the scale is terawatt hour. from low carbon source, we see that the share from this source are still very low when compared to all other sources. In the case of China, USA, and Brazil, and Russia, that I will show in the next table. Please, this table here is the top 10 countries in using low carbon energy. In the next table, come here, I present the top 10 countries in the complete production of energy in terawatts hour. Okay? Then we can see that the contribution, the share of the low carbon energy in these countries are very low. China 16%, United States 16%, almost global. Canada and Brazil it was somehow higher, but we have here the contribution, a very strong contribution of hydropower. France, as we have seen, is nuclear. Russia, also the share of low carbon source in Russia is only 13%, but the biggest contribution is nuclear and hydropower. Okay, then let's now consider the technical scientific aspects. As I have said in the beginning, I will show to you 3 different branches of technical scientific aspects. The first one is about efficiency. Okay, no one doubts, everywhere knows that over the last few decades, we have had a huge increase in efficiency in all industrial process, in the means of transport, in our domestic appliance, in house construction, and so on. The following sequence of graphs that I will show to you translates this astounding evidence. It follows then the question about what is the motivation in change the energy system, because we have had a so high increase in efficiency. And this is somehow a strong cause of this slowdown in the energy transition, certainly. Look at this graph. This is what we can call the energy intensity use. Energy used in the last 50 years in units of kilogram of oil equivalent per $1,000 GDP. We can see that this energy use reduced about 30% in 30 years. Okay? And we can see that this reduction is really impressive. We can't produce the same wealth measured by $1,000 GDP. We can produce the same wealth with 30% less energy. This is the point. Now, for the United States, the fuel economy in United States cars. We have had an increase of fuel economy since the 60s, 70s. An increase of 70%. And this picture is not different for European cars or for every car now rolling in the world. We have a very, very high increase in the consumption. The same phenomenon happening in the aircraft fuel consumption per seat. This is a picture of mine. I work with aircraft construction, aeronautical engineering, and I calculated the consumption of the reduction of fuel consumption in jet engines during the last 50 years. You can see that when we compare with the beginning of the jet aircraft, commercial aircraft, we use now only 25% of what was necessary in the 60s, for instance. That is a very significant reduction in fuel consumption. Okay, then this remarkably increase of efficiency all along the last decades, a phenomenon that economists frequently coin as decoupling, has contributed for the observed delay in the adoption of the new low-carbon energy source. Now, I will speak to you about the technological drawbacks. We will see there are now 4 very important technological drawbacks, okay, provoking as causes of the slow pace of adoption of a renewable source. The first one is what I call the obsession on controlling the planet's temperature. This is a very bad science. We know that climate change is a very complex issue, and there is no complete agreement among scientists how the human action will influence the Earth's climate. Politicians are not scientists and are making decisions based on very controversial subjects, such as what is the difference between temperature measurements and temperature anomalies, the difference between climate and meteorology, and above all, based on climate models that until now have proven to be ineffective in forecasting and don't explain anything. All the discussions that we see in the IPCC meetings are focusing on establishing a limit for the heating of the planet temperature between 1.5 or 2.2 degrees percent. Everybody speaks about this. Né? We must limit the temperature increase of the planet. But this is somehow a chimera. As if there were a thermostat that we could set the desired temperature. Such thing does not exist. No? This is idiot. Opinions differ on what is the true relation between the concentration of CO2 and the temperature of the planet. There is not an unanimous opinion about this correlation. It's still about the problem. We know that human influence have increased 5-fold, the human action since the 50s, and the Earth has warmed modestly. The most severe, but we can say that the most severe weather events remain within past variability. And there is a plenty of geological evidence and records to attest this fact. What is happening today already occurred, most of them occurred in the past, mainly regarding warming. We can speak about a chimera of carbon neutrality. And why? Because science shows us that the concentration of CO2 in the atmosphere increased by about half of the amount emitted annually. Since the annual concentration is 415 ppm, when we emit 37 billion tons of CO2 annually, the current measurement, this concentration will increase by about 2 ppm. But it's important to consider that the concentration of CO2 is the result of cumulative emissions. And this concentration will not disappear when we stop emitting. It will remain there for centuries, being slowly absorbed by plants and oceans. Thus, a modest decrease in emissions will only delay, but not prevent, the increase in concentration. Now, about our second drawback, about the seasonality, environmental consideration, and generation capacity, mainly from solar and wind energy. In discussions about renewable energy sources, mainly solar and wind, we can observe that there are some important objections, such as those related to seasonality, electricity generation capacity, high storage costs, and low levels of efficiency. And even the fact that both require a lot of space to install. About seasonality, we know the fact that wind flows and sunlight are intermittent, and in this way, both are largely dependent on local weather conditions. Power generation from windmills and solar panels cannot be scheduled in advance because the wind, we know, does always blow and the sun does always shine. It's evident. Unlike natural gas or coal, we can store up wind or sunlight to use them when needed to produce electricity. And besides the short-term local fluctuations, wind and solar power generation follow the seasonal cycle of the weather. We can add that wind power generation in winters is much stronger than during summer, it's evident, and solar power generation in summer, on the contrary, produces much larger yields than during the winter. And there are many criticisms regarding the huge areas needed for the installation of solar energy plants, as well as the visual pollution caused by wind energy generators. We know that we have an investment of 4.5 billion US dollars in the last decade. And the result of this large, huge investment was the growth from 1% to less than 3% of the worldwide energy supply in wind and solar energy. Look now at this graph. Here is the production in terawatts hour of the main low carbon energy source. The black one above is hydro energy. We can see that hydro energy has grown a little bit. Nuclear has the blue line remaining more or less constant, and solar, the red line, and the wind, the green line, has grown a little bit, but only significantly after 2010. Compare these numbers with the worldwide energy production and consumption. It is about today 144,000 terawatts hour, or 144 petawatts hour. In the next slide, I will try to show to you what is the meaning of these numbers measured in terawatts hour. Let's make some calculations. We focus on a typical town with 1 million people in developed countries. A typical household in the United States, in Europe, consumes about 800 kilowatts hour a month. But attention, only in households that have all electrical appliances, okay? This is, for instance, not my case, because I use gas and electricity. My consumption is about 300 kilowatt hour. Okay, then consider that each household is 2.5 people. This is the mean value in Europe. That means that a million people town has about 400,000 houses. But we know that residential consumption is about 65% of the total energy. The rest of this energy is necessary for commercial and industrial purposes. Then, making some calculation, we multiply the number of homes by the yearly consumption, and we get about 1.15 terawatts hour, a typical consumption of 1 million people town. We know that, for instance, a top wind turbine delivers about 10 megawatt power. And if we multiply this by the number of hours in a year, supposing that the wind turbine can work all the whole year, we get this number, 86,400 megawatts hour. Then, if we divide the energy necessary for a town by this power delivered by one wind turbine, we find that we will need 11,600 wind turbines to supply energy for a million people town. But attention, we are speaking about consumption, which is only about 1/3 of the production due to losses in generation, transmission, distribution. That is then the number must be bigger. Okay, then in this table, I show to you the biggest wind farms in the world. You can see that the biggest one is in China. Look at the last column, the huge number of wind turbines that they need. And occupying a surface of some 100 square kilometers. We know that there are now around 400,000 wind turbines across the planet, on land or at sea. China is by far the world leader in installed capacity, with a share of about 30%. United States comes second with 13%. However, regarding the annual growth rate, China led with a share of 56%, followed by the United States. The table in the previous slide presents the 10 largest wind farms on the planet. And as we can see, 2 are installed in India, 4 in the United States, 3 in the United Kingdom, and the most powerful one is located in China. But let's think, considering this table, let's think about the payback. What is the capacity of these very, very large wind farms? Onshore or offshore? We know that there is a response for the problem of visual pollution and availability of continental areas. Offshore wind turbine electricity generation came in the last 20 years as an optimal solution. But their installation is an intensive, time-consuming, very complex and costly investment for a very small payback. I will give you an example. Offshore installation of wind turbines is much more complex operation than onshore, as it involves the installation of jacket foundations for each wind turbine, the logistics of transport all components to the site on the sea, jackets, towers, airfoils, nacelles, substations, and so on, to which follows the complicated operation of assembly of all these in the midst of the maritime agitation. I give you an example. A very small park. It was not included in our table because it's a little bit smaller than the last one. East Anglia One Park, located 43 kilometers from the eastern coastal line of United Kingdom. Okay, look at the cost, 2.5 billion pounds, and was a 10-year-long project, occupying a lot of space. It consists in 102 individual wind turbines with a power capacity of only 7 megawatts each, but spread over a surface of 300 square kilometers. Just to have an idea what surface is this, this is bigger than many middle towns in Europe. It's bigger than Lisbon, bigger than Amsterdam, bigger than Brussels, for instance. And their nominal capacity is only 714 megawatts, delivering energy sufficient to supply about 600,000 homes during a year. In other words, we can say, this is so much for so little. The story is the same for solar energy. The worldwide installed solar photovoltaic capacity grew significantly in the last 2 decades, as I have shown in the graph, from less than 100 terawatts hour produced in 2010 to now about 1,000 terawatts hour produced in 2020, with 138 gigawatt of new power capacity installed in the same year, that's in 2020. This staggering growth in solar photovoltaic capacity is being distributed in large, medium, or small-sized solar parks, mainly in flat and desert regions, and we know on the roofs of the houses and buildings in big cities of small villages around the world. But let's look at the following table. Here are the top 10 solar parks in the world. Look at the value of the energy delivered. Okay, it's not so significant when we compare this with the size of the area necessary to the installation. We see this almost an area for a small town, a town with 100,000 people, for instance, or more. We see, for instance, the 2 last one in China, they take a surface of 90 quadrat kilometers. This is almost the size of Lisbon. The largest solar park in 2020, with a capacity of 2.245 megawatts, is spread across about 60 square kilometers. Is located in India, near the Pakistan border. It can supply energy for a population about 800,000 households. Okay, this is a big farm, but it can supply energy for only in one city. This concentration of energy production in places very far from population concentration involve another aspect, the very complex logistics of energy distribution and storage, and a lot of losses in the transmission. And in the end, there is an occupation of surface too large for the final benefit of supplying energy to a single town, even if regional. That is, we need to install a solar park with the size of a town to deliver energy for another town. This is crazy. Also consider the fact that the availability of a desert climate area is necessary for the installation of this type of solar parks. And such conditions is not available in everywhere for all countries. We need desertic regions. My question is then, how to supply the entire planet, or at least a significant part of it, with solar energy? So now to technological drawback number 3, about transport electrification. We have here really a huge problem, because electrification is an essential part of the structure of modern society. And when I speak here in transport systems, I speak on transport on land, automobiles, aircraft in air, and ships, transport on the sea. This graph shows the unfolding the evolution of the number of electric vehicles in millions during the last 10 years, more or less. We can see here at the end of the graph that in the last year, we have an addition of about 3 million electric cars to the worldwide fleet. But consider that currently, we have about 1 billion cars in circulation, and the electric vehicles made up only now about 3% of yearly car sales. Okay, this exponential worldwide increase in the automobile fleet, which is also being modestly accompanied by other means of land transport, vans, trucks, and buses. The leader of this explosive growth was China, with 44% in 2021, followed by Europe, 31%, United States, 70%, and all other countries contributed with just about 7%. China also dominates the electric bus and electrical commercial vehicle deployment, with its stock reaching now about 500,000 buses in 2020, about 98% of the global stock, and 250,000 electric light commercial vehicles. That is about 65% of the global fleet. Okay, but when we make some calculations, we find that it will be necessary to keep a growth rate of about 100% a year in order to reach the target of net zero emissions from automobiles by 2050. In my view, it will be impossible to reach. Looking to the graph presented in the sale of cars, we might think that such a goal will be achievable, perhaps, but most analysts believe it is impossible because there is another important bottleneck to overcome. This is the production of batteries. That's our next point. But regarding electrification, there is much more troubles in the horizon. Now, until now, we have spoken only about automobiles. But transport is much than that. It is worth to note that our need for electrification is not limited to cars, but also to airplanes and ships. In other words, to two very important transport sectors, aviation and maritime transport, responsible currently for about 2 to 3% of global CO2 emissions. But projections to 2050 estimate that this share can reach between about 20% in the coming years. Aviation and maritime transport. Okay, we know that so far shipping is the only transport sector not subjected to international greenhouse gas emissions reduction targets and policies. We have observed only some occasional progress in Nordic countries, Denmark, Sweden, Norway, not necessarily to satisfy regulations of any kind, but only with the aim of reducing emissions in relation to the transport of passengers on regional trips. It's all progress that we can see in maritime transport. And this is just a drop in the vast ocean of the gigantic maritime transport sector involving the immense cargo ships, oil tankers, cruise ships, and so on, responsible for the immense pollution of our oceans and coastal regions. We know that currently 90% of world trade is carried by about 90,000 very large ships. And it is very difficult to imagine that this entirely immense fleet could be converted to electric propulsion in the next 20 or 30 years. Not to mention the monstrous number of powerful batteries that will be needed to fulfill this goal. Interesting to observe that regarding aviation, the scenario is very different for two main reasons. Firstly, in the bandwagon of efficiency paradigm that I have discussed with you, airplane constructors have made a significant effort to increase the efficiency of flying over great distance, not only through the development of more efficient engine engineering, but also through the development and intensive use of lighter materials, such as composite materials that are now used in aircraft construction. Secondly, we can mention direct market mechanism.
Devezas, можно я чуть-чуть вмешаюсь? Смотрите, я посмотрел вам еще 15 слайдов примерно, да, и где-то у нас минут 10 осталось по времени, вот, чтобы вы равномерно, чтобы там выводы не сжать, а там их полноценно рассказать. Вот, может быть,
Okay, thank you.
Спасибо.
Secondly, we have the direct mechanism, then the aviation industry and have imposed serious restrictive measures to reduce greenhouse gas emissions. And since the 1990s, the International Air Transportation, the International Civil Aviation Organization, established a series of very strict targets for reduction of emissions that has been reasonably accomplished. But very important, such measures concern the reductions of emissions through, again, inefficiency in all types of aeronautical operation, and not the ambitious task of zero emissions through the elimination of fossil fuels. That is, in other words, aircraft construction, aircraft engineering today is not thinking seriously in changing the system of propulsion. What they are looking for is just the reduction of emissions through, again, inefficiency. So I go ahead with our last point, the fourth point, the material shortage. I will speak just quickly about this because this is still ongoing resist in our project. But the fact is the full implementation of photovoltaic cells, windmills, and mass use of batteries for propulsion. It is necessary to use a series of very critical materials, many of them rare earths, which until now have never been used in large scale. I add to that the very important aspect that practically the same set of materials are needed to produce our digital equipment, such as computers, smart TVs, and smartphones. Some examples of critical materials, we have lithium, cadmium, copper, gallium, germanium, and so on, and a collection of rare earths, cerium, neodymium, praseodymium, dysprosium, terbium, etc. So, I have not time to make considerations about the material shortage, but it is very important to show that for the future transition, a green transition, we have serious problems of material shortage, not only because the materials are rare, but because they are very costly to extract, and because they imply in political problems, that because the distribution of these elements on the earth is not equally distributed among the countries. So I will jump this. I will show this here for you. The numbers associated with this new green material needs are mind-boggling. For instance, we need 8.5 tons of rock are needed to produce a kilogram of vanadium. We need 50 tons of land for produce 1 kilogram of gallium. We need to move 1,200 tons for production of 1 kilogram of one rare earth, lutetium. Then when we look at a car battery, we know that a car battery weighs about a half ton, 500 kilograms, the volume of a suitcase. It contains about 12 kilograms of lithium, 30 kilograms of nickel, 20 kilograms of manganese, 15 kilograms of cobalt, and so on. Inside, we have about 7,000 lithium-ion cells. In other words, to make a car battery, you must produce 10 tons of brine to produce lithium, 15 tons of ore for the cobalt, 2 tons of ore for nickel, and 12 tons of copper. A total of 200 tons we need dug up from Earth's crust for a single battery. And when we extrapolate this to 1 billion vehicles, we see that we will need to move 200 billion tons of ore, or about 125 billion cubic meters of soil. Really a gigantic, huge amount of land. So I have not so much time for this. About this problem of material, I left here this in green, the last question. How green is the green transition? Because we know that this huge amount of materials are being extracted and refined using coal, oil, and gas. In other words, using our fossil fuels, coal, oil, and gas. We don't produce materials, we don't refine materials using solar or wind energy. So, about technological improvement, is there some hope? On the other hand, we have the opinions of some optimists. They argue about the unabated technological improvement, observing deployment of renewable energy sources that may contribute to some stimulation of the takeover process. The main argument of these people is that solar and wind energy production have improved dramatically and will continue to improve. Okay, but we need to consider the sharp decrease we have observed in the so-called levelized cost of electricity, which consists in a suitable measure to planning and installation or expansion of electric grids. Then, when we look to this graph, here's comparison between the fall in the levelized cost of electricity for solar, the red line. In the green line, you see the reduction in the offshore wind. In the brown curve is onshore wind. And then for comparison, we have the cost of hydro energy. Then the conclusion of when we look to this graph is that we clearly see that levelized cost of electricity for renewable source is already leveled to an almost constant level, and it is not expected to reduce significantly for the next few years. They conclude that compared to continuing with a fossil fuel-based system, a rapid green energy transition is likely to result in trillions of net savings. But there is a fault in this conception, because a model for energy transition must contemplate the enormous difference between nations. And this is impossible in any developed model. We cannot develop a model for the future of energy transition considering the difference between countries. This must be done only country by country. And the most studies that I have found consider only the United States or some countries in Europe. In other words, if we can have a gain of $1 trillion or $1 billion, I don't know exactly, but we can say it cannot be distributed equitably among all lands concerned. So, finalizing, I will shorten my conclusions, just the most important conclusions. First, it is important to consider the two most crucial aspects or obstacles provoking the slowdown of so-called green transition. The first one is that the intended reduction in emissions is occurring in a context of increasing demand for energy, whether driven by population growth or by the fact that developing economies intend to catch up with developed countries. Add to that the existence today of the still immense reserve of oil and gas. And as I have showed to you, there are a series of drawbacks in the development of intended low-emission technology, mainly when we speak solar, wind, and the batteries for propulsion. Solar, wind, and batteries, they need a lot of energy to be produced. and until now, they are mostly produced using fossil fuels. They disturb significantly the environment, either by its production or by its use, and require a massive use of limited and rare natural resources. Okay, thank you very much. I can conclude my presentation now, and I am at your disposal for.
Так, вопросы. Юрий Анатольевич Плакиткин, первый вопрос.
Да, спасибо. Профессор Плакиткин. Во-первых, профессору очень большая благодарность большая за поднятую тему. Она действительно, мне кажется, очень важной. Вот. И у меня в связи с этим три вопроса. Собственно говоря, они три на базовое понимание, вообще-то говоря.
Sir, thank you very much for this very important and very interesting report. There are several things I wanted to check and clarify. Indeed, lots of experts lately have been talking about energy transition, and they seem to be using different definitions. What is yours? How do you define energy transition? Is it for you the same as a switch to green technologies, or does it include anything else? Thank you. There will be more questions.
I have not understood exactly the meaning of your question. You are asking about the difference of green transition of energy transition, is this?
Yes, what is your definition of energy transition or green transition? Can you please define what it is for you?
Okay. Green transition for me is the thinking that we need to abandon completely fossil fuels and jump to the low carbon energy source, like wind, like solar and batteries. This is what I call, everybody call green transition. Energy transition is another thing. Energy transition is, for me, the search for the most suitable mix of different energy sources to the future in order to not emit it so much, to bridge it so much the environment. And when we speak about energy transition, I am not thinking, for instance, only about wind, solar, and batteries. I am thinking in the mix, for instance, considering nuclear, carbon absorption, carbon capture, biomass, hydrogen, the economy of hydrogen. This is we need to look for the best mix in the future. This is energy transition, not necessarily green, because green it is not, as I could try to demonstrate, because for the real green transition, we need to move a lot of sand of land. We need to occupy a very large surface of land and the very other political problems and so on. Every country should choose really the best mix of energy for the future, even if we need to continue to use gas, for instance.
Да, спасибо, я понял вопрос, и я солидарен с этим ответом. Могу ли я задать второй вопрос? Второй вопрос, вот, собственно говоря, продолжение моего первого вопроса, тоже касающийся понимания общего, методологического понимания.
Thank you very much, sir. I think I fully concur with what you said. And let me ask you my second question. You posit that social, economic, political, and technical factors, they all impact the energy industry. But how do you know that this relationship works in this direction? Maybe it's the energy sector impacting the technological factors, not the other way around. Think, for example, about the previous industrial revolutions. The first industrial revolution would not be possible but for coal. And the second industrial revolution only happened when oil was discovered. So if we imagine for a second that this relationship works in the inverse direction, then we would have to revisit a lot of your findings. What do you think about that?
So we had, thank you very much for the question. We had more than 2-3 energy transitions. Exactly, we have the first transition was wood for coal. Then we had transition for coal to oil. Then we have the transition for oil to gas. And I have demonstrated, I have mentioned my paper from 2010. I have demonstrated that in between in the 70s, 80s, and 90s, we have an increased efficiency. And I have shown that we have an energy transition, another revolution. That was the transition for oil and gas, fossil fuels, for changing for efficiency. This in between, but with now the new digital revolution that is happening now. Then we are almost in the limit of at the end of this new energy source that I am talking that in efficiency was a kind of new energy source that evolved during the 80s, the 90s, and in recent years. And the real necessity for the new energy transition is occurring only in the last 20 years, since the 90s, for instance, because we are now only after 1990, after the beginning of the discussion of the IPCC meetings, is that we are really looking for new energy sources. This have never happened before. People in the previous energy transitions, the people have not looked for the transition. You understand what I mean? Okay, then we have the succession: coal, wood, coal, gas, fossil fuels, and now efficiency. And now we are looking for the new energy sources. This is the first time that mankind is looking for the necessary energy to feed the planet. This is a very different situation.
Спасибо, я с вами солидарен. И если мне будет позволено потом после вопросов выступить, я даже солидаризируюсь как-то с вашим мнением, высказав свое.
Thank you very much, sir. I do concur with what you said, and I would actually like to make a short speech later on if time permits. In the meanwhile, I have a question about the future evolution of renewables, because in your speech you talked a lot about challenges for wind and solar, such as the fact that solar requires a lot of space and there are energy accumulation issues. But what if, for example, we establish an array of solar panels in a geostationary orbit? That would take care of most issues we have, wouldn't it? What do you think of this maybe futuristic take on the evolution of solar power? Thank you.
Of the solar, sorry, I don't understand. Solar power for what?
The question is, how do you see, you see lots of challenges with solar power. Do you also believe there is still a lot of evolution possible, a lot of prospects to solar power?
Okay. Thank you. Thank you very much for the question. Well, I am not a specialist in solar voltaic photovoltaic cells. I am reading since some years about the evolution. Maybe we can have some further progress, but for the time being, for instance, I know that the third generation of transformers, né? They use new semiconductors, but these new semiconductors use very rare materials. And that is the problem. The bottleneck in every technical evolution in this sense meets the obstacle of the necessary materials, because we need some phosphates, we need some rare materials to further development of solar energy, or for the increasing performance of the solar voltaic cells. I do not see a bright future for solar energy on land, on the earth. This is different from space, okay? In space, and perhaps in the solar colonies, in the moon, or even in Mars, okay, we have some prospects that can be very useful. But solar energy to feed, to supply the necessities on Earth, I sincerely do not see a bright future for this.
Да, я с вами согласен. Не буду развивать дискуссию, для этого специально будет отведено время. Только хочу одну заметить фразу. Если бы это случилось, то количество...
Yes, thank you very much. And I'm also thinking that, if that actually happens, we would certainly require significantly fewer materials.
Коллеги, у меня просьба, кто в Zoom хочет задать вопросы, пожалуйста, там отметьтесь, там руку поднимите, или там как дайте о себе знать, или напишите. Так, я вижу в зале, да, у нас еще есть Tsibulsky, да, пожалуйста, нажимайте кнопочку, и вот вопросы покомпактнее, чтобы переводчику было удобно перевести, либо избирательной части. Да.
Любой способ энергопроизводства влечет за собой последствия экологического характера, включая и... Спасибо.
We all know that energy production always has some environmental impacts. And it's true for renewables as well. I'm not just talking about environmental impact at the level of manufacturing. I'm also talking about the level of operation. Have you seen any research into how wind farms change the dominant winds around them? Thank you.
Okay, thank you. Your question is if I know the effects on the environment of wind farms.
The question is whether you have seen any research into that, research on how wind farms change prevalent winds.
Yes, I have read some. I have read some few papers about this, but what is the problem? I cannot understand really the objective of the question.
Can you recommend any articles of that kind?
Okay. No. I know only reports from IRENA. You can see a lot of reports from IRENA. IRENA publishes every year a balance of the evolution of wind farms and solar farms around the world. This is really a very recommended suggestion to read the IRENA reports.
Мы продолжим это. Мне кажется, еще часть ответа была то, что в тех публикациях, что профессор читал, не было вот этой вот связи, влияния на розу ветров.
Я просто тогда поясню, может, не точный перевод. Большие гидроэлектростанции – это большие водохранилища, это локальные изменения климата на данной территории. То же самое возможно и с размещением больших ветряных полей, ветрогенераторов, которые изменят характер климата на конкретном.
Sir, let me rephrase the question. We all know that large hydropower plants, for example, have a significant impact on the climate around them. Well, because usually they have large reservoirs established next to them. I'm wondering if the same happens with large wind farms. Small wind farms obviously should not have much of an impact, but a large wind farm, I'm guessing, should possibly change the prevalent winds in the area, and that may lead to a change in climate. What do you make of that? What's your position? Thank you.
Okay, thank you. Now I have understood your question. Thank you very much. Really, I have read something about the very large wind farms disturb the distribution of wind around them. But I would say this is another drawback of very large wind farms. I have read some reports about this, also from IRENA, some criticism about, and maybe I read something about this, that the solution in the future, first is the installation of them in offshore, in order not to disturb the environment on land. But there are other critics about the perturbation of the jackets of this wind turbines on the sea, disturbing the bioequilibrium in the sea. I say that there is a lot of critics about wind energy, but the main problem about wind energy is just the power capacity. What I have tried to show some numbers about the power capacity of a wind farm. Very large wind farms can deliver energy just for small countries. Okay, let's suppose that we have no problem with the environment. Okay, let's abandon the environment. No problem. But the return, the payback of the very costly installations of these wind farms or solar farms are very small. The payback is very small. This is much on the contrary of hydropower, for instance. We have really a very big disturbance of the environment when we construct hydropower generation. But the payback is immense. The very large Iguaçu power plant in Brazil, in the border with Brazil and Argentina, it disturbed the environment, the region, but they deliver energy for all South Brazil, about, I think, 40 million people, just one power hydro plant.
Спасибо. Окей, да, у нас тут внутренняя дискуссия английский-английский получилась. Так, коллеги, есть еще вопросы? Я хотел два вопроса задать, я видел еще в чате один вопрос. Я тогда два своих вопроса задам. Мой первый вопрос стоит следующим. Я вот слушал доклад профессора Деvezasa в Петербурге, и мне очень понравился тезис о том, что многие эксперты, многие исследователи путают климатологию и метеорологию. Вот попрошу, вроде бы это должно было быть в слайдах, да, попрошу.
Sir, I have two questions of my own. Let me start with this one. I really enjoyed your presentation in St. Petersburg, where you said that lots of experts confuse meteorology with climatology. What do you think is the main difference between them? Like, how do you draw the line between the two? And a question which is related to this one is that I actually want to hear your feedback on my hypothesis. I personally believe that had the world chosen to embrace energy transition in a slower, more step-by-step way, total emissions would have been lower. Because right now, what we see is the whole world more or less striving to effect this energy transition as soon as possible, incurring huge costs in the process. Maybe if the process were slower, but we also transferred all the technologies to third world countries, and well, we just took our sweet time to do that, total emissions across the whole process of energy transitions would have been lower. Thank you.
Sincerely, I could not understand all the complete question. But what I can say about this is that the energy transition will happen anyway. The problem is that it will be not so quick in 2050. As we wish and as the IPCC meetings are discussing. I think it is impossible that in 2050 that we have zero carbon in the atmosphere due to a lot of reasons. One of them is that I have commented on because I cannot remove the carbon, the CO2 that already is in the atmosphere. This is the first problem. Another problem is that the most of the aircraft, automobiles, and ships that are being produced now and delivered in the last year, for instance, Boeing has produced 450 aircraft. Airbus has produced 670 aircraft. All these aircraft are produced to be used during 30 years, at least, to have a payback. That is, in the next 30 years, all these aircraft and ships that are being delivered now will be running using fossil fuels. That is, in 30 years, in 2050, all the aircraft, many of the today's automobiles, and many of the ships today delivered will be running using fossil fuels, because there is no way to change for instance, for the aircraft to change the propulsion. May be possible in ships. We can transform a ship using nuclear power, but I don't see any comment, any discussion about this in the IPCC meetings, for instance. I never seen any exigence of the IPCC meetings on the ship transportation. This does not exist. Then, as I said at the beginning, I believe that we will have the energy transition, but complete zero emissions, carbon emissions, if this happens only by 2070, 2080, not before.
Спасибо, да. Я тогда в дискуссии выскажусь. Второй вопрос. Можете ли оценить вот?
I believe that you are somewhat skeptical, let's put it like this, of fast energy transition. How many other researchers, in your opinion, are like you? What is, in other words, the share of skeptics when it comes to a fast concept of energy transition? Thank you.
Thank you for the question. Oh, I think a lot. At least many of my colleagues, just an example. I have published a book very recently, two books in spring, with a collection of 26 chapters from very different authors. And I can say the content of the whole book is transmits the idea that even the forecasting chapters, that the many people are very pessimistic about this, or they have the same idea that I have. Mainly, some scientists that besides the technical problems that we were seeing, they are considering also the political problems they are living today. This competition with China, this is going not very good. This competition, Russia and also in the Western countries, I don't be, this will contribute for the things is not running so good as we wish. As I said before, the transition will happen, but I have demonstrated this in this presentation. We have so many different troubles to overcome that I don't see any quick solution of this about this. And when we add to all these problems that I have shown to you, or the pure political problems and the actual circumstance in the world now, sincerely, I am very pessimistic, and I can say that many other scientists have the same idea as I have.
Can you hazard a specific guess, like would that be 20% of skeptics, 30%?
Oh, no, I don't give a number because I don't know. It's very difficult because it's so the people that I know, I don't know how much they represent in the whole scientific sector. But I am seeing when you look at the books that are being published about this, you can see a lot of books now with a very pessimistic view. Can you change for my computer, the computer in another room? Because
Yes,
I have
okay. We will show that. We will show this.
in my last slide, I have not comment on the last slide. A very recent book that I suggest that everybody reads. I can project the
Просто боюсь, что он будет происходить очень долго. Вызовов так много, что, в общем-то, трудно оставаться оптимистом в таких условиях. Когда вы попросили дать более точную оценку, я отказался это сделать, потому что я не понимаю, насколько репрезентативен мой круг общения. С другой стороны, даже не только в научной сфере, я вот на последнем слайде своей презентации привел фотографию недавно вышедшего бестселлера, написанного с точно таких же пессимистических позиций. Кстати, на мой взгляд, очень хорошая книга, всем рекомендую прочитать.
Так, коллеги, кто еще хочет? Вот я смотрю, Александр Владимирович Кейко, да?
Да, Валерий Валерьевич.
Да.
Вот, спасибо профессору Деvezasу за его такой всесторонний анализ. Он в начале своего выступления упомянул, что решения, которые должны простираться на полвека вперед, принимают в основном старые люди, которые в силу психологических причин не могут адекватно думать на далекую перспективу. Но мне кажется, что мы сейчас стоим на пороге...
Thank you very much, Professor Devezas. And as regards the book, we will show the book from your presentation a bit later. But now the question from Alexander Keiko. So you mentioned that key decision makers today tend to be older people who cannot think long term. Aren't we facing potentially a different challenge when the generation of green transition fanatics comes to power? They will be prepared to sacrifice prosperity and whatnot for green transition. Do you think it's a veritable challenge?
Yes, a very, very good question about this. I touched about this in the beginning of presentation. Not the generation, next generation, perhaps not yet, because we need some few solutions that are not in the horizon. For instance, I think they may be green transition fanatics, but they cannot solve the problems of materials availability, for instance. In my view, the real transition that this next generation can bring about is only if they realize the possibility of hydrogen fuel cells, one point, and the second point, nuclear energy. This is the most cleanest energy that we can produce with the knowledge that we have now. And that is a very easy technology to transmit to the next generations because it exists now. Then answering to your question, if the next generation can perform this transformation, it is really a possibility, but they need to solve the problem of materials, for instance. And the only way to solve the problem of materials is not using the materials. And what is the solution for this? Nuclear energy and hydrogen fuel cells.
You know, my concern is that climate fanatics will try to enforce policies lowering consumption.
To curb the demand.
Will try to curb the demand.
Yeah, this is a possibility, but there is another point that we can say that not the generation in charge, but the next generation. I see this in my son, in my grandsons. They are not so consumers. I was, and here's my father or my mother. I think the new generation is far less consumers than we had. But anyway, the economists have the fixed idea, the economic growth should continue. They measure, oh, okay, the country is being very good because they are increasing 4% a year. Okay, Europe is not so good because it's increasing only 1% a year. That is the mentality that economic growth is necessary is still exists. And this is a problem. We need really to abandon this concept that economic growth is a good measure for the success of a nation. This is a very, very important problem, economic problem, that I cannot see solutions for this.
Спасибо, да. Коллеги, я предлагаю перейти к сессии выступлений. Можно посчитать, кто хочет выступить, чтобы мы спланировали время. Двое, Юрий Анатольевич, так, есть у нас еще? Там был еще вопрос от Валентина Владимировича Данилова из Новосибирска. Но он, как я понимаю, я бы не хотел его зачитывать. Если, может, он сам здесь готов его задать, мы бы его послушали. Ну, я бы сказал так, вопрос, который на самом деле вот в поддержку доклада, да, о том, что, да. Валентин Владимирович, вы дадите вопрос?
Спасибо. Хотел бы поприветствовать всех участников семинара. Но я думал, что вопрос, когда задан письменно, то проще его перевести, но я его зачитаю. Значит, председатель Комитета по климатической политике и углеродному регулированию Российского союза предпринимателей высказал тезис, что выбросы за счет экономической деятельности парниковых газов составляют всего 6% от природных потоков. И он сказал, что гораздо проще, может быть, помочь природе эти 6% связать, чем бороться самим, так сказать, используя новые технологии и другие.
Thank you very much. I'm happy to welcome everybody. This is Valentin Vladimirovich. And my comment is like this. It has been mentioned that economic activity only contributes 6% to total global emissions. And helping the nature capture a comparable amount should be much easier than trying to bring our, total environmental impacts down to zero. For instance, in Russia alone, there are 50 to 100 million hectares of agricultural land that is not being used. And for all I know, we could have a joint project where we sow, say, miscanthus or hemp or linen or some other technical crop there. It doesn't even have to be trees. It can be grass, so to speak. And it does a pretty good job of capturing the CO2, and it can also be used for, manufacturing purposes in textiles or whatever. For all I know, it could be a joint project with Portuguese entrepreneurs. And then we don't need to interfere with the power sector at all. What do you think of that?
1 billion ton per year of CO2.
Yeah, that would capture 1 billion tons of CO2 per year.
Sincerely, I don't know much about the carbon capture. I know that in Portugal, there are some regulations about reducing carbon emissions from some textile industry that you mentioned. They surpass some measure. I don't know how much. They should pay some taxes. But speaking about carbon capture, this is really a very important step in the future. When I spoke about nuclear energy and the hydrogen propulsion fuel cells, I forgot to mention that the very important investment in the future is carbon capture, carbon absorption, because this is really and carbon reduction too. This is really the only way we have to continue to using some fossil fuels, for instance, gas, with a big reduction in carbon emissions, using the process of carbon reduction in the emissions. And I know that in several other European countries, some industries are paying taxes if they not reach some level of emissions of carbon emissions in the steel industry, for instance.
Итак, коллеги, я не хочу устраивать дискуссию по поводу сельхозугодий. Давайте считать вот первоначальный вопрос такой, как широкая трактовка, да, у нас там есть бесхозные леса, там вот, которые нерегулируемы и так далее, да, то есть, условно, есть некоторый потенциал для другого воздействия, коллеги обменялись мнением о нем. И давайте сейчас перейдем к выступлениям по очереди. Юрий Анатольевич Плакиткин.
Я хотел бы поблагодарить профессора за весьма актуальный доклад.
I do believe that this report has already touched upon some very important matters for this country and for this institution. Please allow me to start my speech by referring to some of the stats. The statistics I have, for some reason, are a bit more optimistic. Over the past 10 years, for example, transition to alternative energy, to renewables, appears to be, a bit more rosy. And I have stats for 2022 as well. So growth rates over the past 10 years, 2022 included, for oil and petroleum products have been pretty much at zero, and we are talking about annual average consumption. Now, for gas, we are seeing 2.8% increase per year, but with renewables, we are seeing indeed very strong growth of 3.7% per annum. So this is the pace I'm seeing. And it sounds like it's global figures. At the same time, I absolutely want to agree with some of the statements made by Professor, but I will also indulge in arguing with him a little bit. There is no doubt that lots of factors impact the economy. And the energy sector is impacted by economic, political, technological, social, and many other factors. And in present unstable and challenging times, which they certainly are for some countries, in times when our long-held assumptions of what the economy is and how political agreements work are upended. So if we actually manage to disregard all those political and economical and other considerations, we will see what the real foundations of our lives are. And these foundations will be the matter, the time, space, and energy, for sure. I believe that energy is, the very foundation of the economy, and it plays a very important role in economic development. There is not a single sector in the economy that wouldn't use energy. All economic sectors consume energy one way or another, which means they depend on energy one way or another. So in this time of a great political divide or economic divide is, in my opinion, somewhat rhymes with the energy transition, which is certainly happening. I actually asked a professor for his definition of energy transition for a very good reason. The reason being that lots of experts talk about it now, and they offer different explanations. Some people talk about energy transition as a climate thing, so to speak. Others talk about energy transition as transition from one energy source to another energy source. And besides this, like local transitions, there is also a global transition, something that we are not really discussing, but it does happen nonetheless. I am referring to the change in the calorific value of the fuel that we're using. There are different ways of calling it. You can, for example, talk about energy density per, say, gram of mass. It keeps growing, went from grass to coal to oil to gas, all these energy sources. Actually have very different calorific value. For firewood, it would be 0.2, for coal it's 0.7, for oil it's 1.44, for gas it's 1.8, and for hydrogen it's 4. So this calorific value is actually, it actually follows a log curve. And the max for this curve would be driven by Einstein's formula of E equals mc squared. This is the pinnacle to what the humankind strives for. I think that there are actually three elements to this curve. One is the lower plateau, then there is vertical escalation, and in some distant future, there will be another plateau, the top plateau. So I believe that humankind currently sits at the inflection point. We are about to go from this first plateau to this, vertical section of the curve. Well, the whole history of humankind has been the history of increasing calorie value. Why would we want to do that? Why would we want to increase energy density? That's a rhetorical question. Any type of energy, any type of fuel propels machines contraptions, devices used in the current paradigm, so to speak. We've actually shown that average speed in the economy is driven not by the calorie value itself, but rather by calorific value squared. So you increase calorie value by a factor of 2, speeds grow up by a factor of 4. And here we're talking about higher labor productivity. And I think that a game like this is certainly worth the entrance price. Now, why would humankind want to embrace renewables, or the alternative energy sector as it's often called? Our calculations show that the calorific value of gas, which is considered, the best one, stands at 1.8. For hydrogen, it's 4. In solar power and wind power, we are talking about 4 to 6. That's actually a significant increase in terms of energy density. So this way, we should be able to significantly increase labor productivity and usher in new technologies. So I do believe that the power sector pretty much drives the level of technological development available to a given civilization. What do we expect in terms of future evolution of this calorific value? Our calculations show that between 2022 and 2050, we will be seeing a transitory stage. So we expect this calorific value or calorie equivalent to grow from 1.2, which is the current average for the global economy, to 2, 3, or maybe even 4 by 2050. And again, I'm talking about the averages here. After that, beyond 2050, we should see further escalation. And here I fully concur with the professor. I think it's going to happen around 2050 or 2060. And my last comment is that I believe that this, vertical escalation segment, so to speak, will rely not just on the energy sources that were mentioned, such as wind and solar. Just like the professor, I am expecting a much bigger role to be played by nuclear, and then hybrids, and finally nuclear fission. Nuclear fusion.
As I said, I like very much your reasoning about the energy density, but there's a problem. When you think about the energy density of coal and coal and gas, for instance, in the previous revolutions, this kind of gasoline or diesel or other fuels that we use, or gas that we use in our homes, we use this energy source is transmitted to us personally, and I use in my house, in my car, and so on, even if the energy density is very low. Then you say, okay, hydrogen has a higher energy density, if it's true. But you said that the solar and wind have higher energy density. This is not necessarily true. Keep attention that the generation of solar and wind, mainly in the big farms, this is only possible in some parts of the planet, in some desertic lands, for instance, for solar farms, on the sea for some wind farms. And they are very distant, usually, from the end consumer. And that means that we have a big loss of energy in transmission, in production too. Then you cannot think only in energy density, because if you think really in energy density, then the most promising energy source is fusion. It will come in the future, perhaps in the next 50 or 60 years. Then, okay. But now, in the situation that we have now, with the using of solar and wind energy, that is the problem, because they can have a good energy density, but they have the problem of first materials, and second, the transmission. This is very different of when you use the hydropower, for instance. That is very easy to transmit this power line, and we have a very big energy density too. Then, resuming, we cannot think only in energy density, because if you think only energy density, then the most promising energy source is fusion, without doubt. Just my comment.
So Yu.A has just said that this is very true about fusion, but hybrid technologies will hit the market much sooner. So by 2050, for sure, we should have something on the hybrid side. This is Mr. Tsibulsky. I think that this whole discussion of some special role of green transition is somewhat artificial. If we take a look at how human civilization develops, we will notice that this process was not smooth by far. And this has been mentioned by the professor, en passant, so to speak. If we look, for example, at specific consumption per capita and compare specific consumption per capita lost in previous century to what we're seeing now, we're seeing much less diversity now, because diversity between different countries in terms of specific consumption used to be a factor of 30, now it's only a factor of 3. It may very well be that the individual countries have been, leveraging their technologies to sort of contain very fast growth of such rapidly developing emerging economies as, say, India or China. And I believe that we are soon going to enter a world where specific energy consumption will not differ much between countries such as, China, Indonesia, United States, or Europe. In this respect, the world will become a much more homogeneous place. Well, how it's actually going to happen is, in my opinion, a pretty difficult process to predict. Some technologies will be washed out, others will remain. But my position is pretty simple. When our Lord created this planet, he chose 3 basic substances that make human life and all other types of life on this planet possible. This is water, air, and sun. So taking this energy, putting it to some self-serving use, different from what was expected or was engineered into our nature, is okay as long as you don't do it much. When you start doing it on a large scale, you will run into irreconcilable consequences. Now, this is what we're seeing, for example, with the hydropower. When rivers cross boundaries of several different states, there is a lot of regulation covering those rivers, and you actually have to come to an agreement with all your neighbors if you want to build a dam there. And now imagine that, say, Denmark builds a wind farm on the boundary or close to the boundary with France, and this way it will sort of consume the wind power that would otherwise be taken up by a French wind farm. Who's going to regulate that? I think it is very important for us to keep this planet, with the factory specs, so to speak. And the way life in this planet is engineered is ingenious. All the natural technologies are part of a larger loop. Even volcanic eruptions that create so much fallout, they produce raw materials, so to speak, for all the other or for many other technologies that our planet has. And I think that we need to be thinking in the same biomic kind of way. Now, CO2 emissions that the world is so obsessed with is a difficult case. I don't think we have a single mathematical model that would be good enough to predict climate for at least 1,000 years ahead. Well, even our current meteorological models are only good for several days ahead. Well, humans have been using wind for many centuries already. Well, you can think of fans and fans, handheld fans in theaters or, ceiling fans. But now people are trying to harness the power of wind on a large scale. I believe that some time will pass and wind farms will be connected to nuclear power plants in order to create a totally different kind of climate, to bring, say, cold breeze to a summer hot Paris, for example. Well, currently, the models we're using are not good enough. They don't really explain how a 0.1 degree change in average annual temperature results in a heat wave in Paris. So we have a population of 8 billion people now. It's expected to grow to what? 10 billion people by the end of the century. I think we can and we should develop a sort of philosophy that will state that humans should not consume more than, say, 2.5 tons of oil equivalent, because the planet will not be able to sustain more. whatever we do, really, even if we fully embrace, nuclear fusion and nuclear fission, that, if we cross that threshold, then there will be horrible consequences. But that, I'm afraid, will require some social and geopolitical harmony. There are lots of players right now trying to preserve the world order as it has been for the last century, which is a shame. I believe that challenges in the power sector are primarily social and political. And we may potentially look for ways of alleviating these problems. Martin Heidegger used to say that nobody really argues that humankind is driven to self-extermination, and only God can save them. So this is where I would love to finish my speech. But I actually thoroughly enjoyed Professor's presentation, particularly on a subject like this. And I really loved it that he touched upon all the issues that I consider interesting. Sergey Beloborodov, and after that we'll hand the floor back to the professor again. Thank you very much for the invitation. Thanks for the opportunity. I also love the presentation. There is one issue, if you like, I would like to stress, something that in my opinion has not been mentioned. And I believe it is actually of great importance. It is nothing serious, really. I will not wax philosophical here. So if we have those CO2 or GHG emissions, and we decide to build a wind farm or a solar farm, will that lead us to a reduction in emissions, or it won't? In preparation for session, I made a short presentation and some calculations. I understand we don't have the time for showing it, but I'll just quote from my presentation here. Now, I looked, for example, at substitution options. So if we take a generation, so a CCGT, oh no, it's not combined cycle, so it's just, a steam turbine. So if we switch it from coal to gas with the same efficiency, we shave off 42% of emissions. So if coal is 100% of emissions, for gas, that would be 58%. Now, if we actually build a CCGT unit there, which has efficiency ratio of 55%, then emissions will go down to 37%. For a nuclear power plant, if we switch coal to nuke, emissions will be zero. Now let's look at wind and solar. Given the seasonality and day and night irregularity, we realize that they cannot really work on their own. They either need accumulators or batteries, or they need to be combined with regular power plants, such as gas-fired power plants. No, they have pretty good efficiency ratios. So in order to produce the same amount of energy with a gas turbine and a wind farm, given the capacity ratio that's average for Russia, emissions would be 41%. Which is funny, because for a gas turbine, for CCGT, that would be 37%. Now, if I'm using solar panels or a solar plant combined with a gas-fired unit, that would be more like 50%, which means that if I switch to gas only, I would be able to reduce my GHG emissions by 63%. If I'm using solar only, I'm shaving off 50%, and I'm shaving it off by 59% if I'm using wind farms together with gas-fired plants. Look at Germany, which decommissioned their nuclear power plants and built lots of wind farms. Had they not done that, had they simply switched from coal to gas, they would have generated much bigger savings of emissions. So the point I'm trying to make is that, solar and wind are suboptimal. If we are really after climate improvement and reduction of CO2 emissions, then we shouldn't really rush headlong into the embrace of solar and wind power. There is another table I have about cogeneration cycle, which is the one mostly used in Russia, where we generate both heat and electricity at the same time, and it's actually officially internationally recognized as a good way of reducing your emissions, compared to first generating electricity and then using electric boilers to generate heat. So let's compare a coal-fired turbine with coal-fired boiler. When we switch to gas, it gives us 42% improvement. And we can go as low as 40% if we're using gas-fired boiler with gas-fired turbine. And if we're using CCGT, it will be as low as 31%. Now, we also remember that Russia has NPPs, nuclear power plants. Now, I can actually combine them. So there are some, older technologies, steam 90 atmospheres pressure. So even if I'm using a coal-fired power plant in conjunction with nuclear power plant, that already gives me an opportunity to reduce specific consumption by 30%. If I combine gas with nuclear, total specific emissions, total emissions go down to 17%. It can be even as low as 8%. So if I want to produce, gas turbines with wind power and also generate heat, that would give me 46% emissions compared to coal and coal structure. With solar, that would be more like 51%. And this gives me a pretty funny conclusion. So if I'm not decommissioning nuclear power plants, if I continue using old Russian CHPs, I can still do 17%, like I can have 83% improvement. And with wind and solar power, I will have 3 times higher emissions. I see there are lots of workshops and various events now around the green agenda and what have you. And it surprises me, because if we really want to reduce GHG emissions, let's do it the best possible way, because wind and solar actually won't take us there. They are suboptimal. Russian energy system is extremely efficient when it comes to heat generation. It is much more efficient than the energy systems of the United States or Germany. Well, in fact, with the exception of former Soviet bloc countries like Bulgaria or Eastern Germany, most European countries' energy systems are inefficient. So if we start building wind plants and solar power plants in Russia, this is not going to result in a reduction of GHG emissions in Russia. It is actually going to result in their increase. So you were absolutely right when you said that proper energy transition may look differently in different countries. Like Germany and Poland and Denmark, they've been using so much coal. So if they simply switch from coal to gas, if they simply install higher efficiency CCGTs, that would give them much bigger improvements. But instead, they're not doing this, and somebody's even blowing up Nord Stream pipelines. I believe this is extremely important. I'm not trying to undermine the importance of other things. There have been very good images taken from satellites showing that currents in the North Sea have already changed. Now, they haven't built all the wind farms yet, but they're already seeing changes. And that's why, some countries are actually saying we gotta actually come to an agreement on how we're going to split up the wind potential of the North Sea region, because it's obviously limited. And it has been very conclusively shown that when you install wind farms, above ground temperature goes up by 1 degree. And, this has been shown by people taking grants through MIT from US Department of Energy. So this is not some anti-green lobby. But their research shows that once you build a wind farm, it already makes things worse by increasing temperatures locally. They say, well, we hope that over time things will improve because emissions will go down. But then they are climate scientists. What do they know about the energy sector? We actually know that in the energy sector, as long as we do not have reliable industrially energy accumulators, they will need to keep, regular power plants running. Moreover, precipitation maps change. Take the North Sea, for example. Some articles claim that, flows are disturbed at distances of 40 or even 150 kilometers. And this means that even the lands, the countries themselves will be impacted because their precipitation maps are going to change, because, all the rainfall is going to happen elsewhere, and that may be a serious threat to their agriculture. This is also something to keep in mind. But I do believe that if we start considering solar and wind power as a part of the energy system, and we also keep in mind that energy consumption is something that is, it happens usually at the same time with energy production. So you gotta generate electricity all the time. We have to recognize that solar and wind power will be detrimental to many countries until we develop reliable accumulation technologies. So yes, we are seeing a lot of new projects in solar and wind sectors around the world. And yes, we are concerned that they're detrimental to many countries. We published this study in 2021, which showed that material intensity with the renewables is 18 times higher than it is for the traditional sector. So the point I'm trying to make is that there are much better ways of reducing GHG. Now, if we're serious about addressing this problem, we should do it differently. If we want to develop wind and solar power, that's absolutely fine. We should give them opportunities to play with their technologies. But why do we do it at such a grand scale? It makes no sense, if you ask me, to stick these technologies everywhere because, as long as we do not have energy accumulation devices, proper ones, it is detrimental. We all know of bad cases in Texas, in the European Union, cases of bad droughts. Now we know that by 2025, Russia is expected to finalize its first program for launching new capacity for renewables, and we will start paying this price as well. I think we don't have much time, so I will like to hand it over to the professor for his last words.
Call him, please.
Сергей Сергеевич, вас тут хотят поблагодарить, вам отнести.
Thank you very much for your extensive presentation. Really, I agree completely with you, completely. But this view of an ideal combination is about what I referred before when I spoke about you. Oh, sorry, this is really when I spoke about the ideal mix. But anyway, there are a problem that you are not considering in your approach. That is, we need a lot of materials in order to implement solar and wind energy. And these materials are very difficult to get. And this is the problem that I've tried to point out. In order to produce, to extract, to mine, and to refine these materials, we need a lot of energy. And we don't need this kind of materials. We don't need the expense in energy if we use nuclear energy or hydrogen cells. There is a big difference. Okay, combining gas, exactly, combining gas with solar, combining gas with wind. Okay, this is a good way to get an ideal mix of the energy production now. But for continuing in the future, this will be a big problem because our planet is a finite planet. We don't have an inesgotable source for samarium, for praseodymium, for neodymium. We have limitations for this. And these materials are very expensive to refine. And don't forget that for the time being, we are using fossil fuels to refine and to produce these materials. This is the biggest problem.
More?
Just about this book. I would like,
yes.
May I speak? I would like to suggest to you a very important book published very recently. That was at the end of my presentation, and I had no time to speak about it. I really suggest you to so then all that I spoke is really about some negative view about the future of the so-called green transition. And then most people now, you can find new books and new publications, and for instance, new names for I suppose that the Green New Deal, the Green Frauds, and the Green Deception. There are many books with these titles. But there is a very recent book with this title, Unsettled, about really what is climate science, what we don't know, what we need to know about this. This man, Stephen Kooning, he is a researcher for the very important research center in the United States, and sincerely, for all books that I've ever read, read about the climate and the climate change in the last years, essentially was the best book, because he is not necessarily pessimistic about the book is not about the green transition or the energy transition. It's just about the today's discussion about what we can do for controlling climate. This is the objective of this book. And I think that most people that are now working on this issue of green transition, of energy transition, should know a little bit more about really what is happening with our climate. They need to know more about climate science. And this book is a very good example, I suggest you to read this book, you that work in this field now. And with this, I would like to finish my comments.